I'm going to do an example with this reaction between aluminum and mercury, going through how to calculate delta G and K. So the first question is how many moles of electrons are transferred per mole of reaction, and you need to answer this question in order to use the equations that are necessary for this. And so if you just look at the charges here, you're going from just pick one of the substances. You're going from 2 plus charges, so 6 plus charges total, to a neutral charge on mercury, and so that takes 6 electrons to do that. If we test it out for aluminum, we're going from neutral to 3 plus charges, and that takes 6 electrons also. So as long as your equation is balanced, which you have to make sure it is, you can figure out the answer to this question for either substance. So the answer here is 6. And so then it's asking us to calculate delta G. And the equation that you need to use for calculating delta G is delta G naught equals negative NFE, the standard cell potential. And I've actually given you that, but you can use the standard reduction potentials to figure it out, but it's given to you in this problem. So, okay, so if we use this, we're going to substitute in the 6 for the N, that's the moles of electrons. And by the way, when I say per mole of reaction, I mean per this unit of reaction. And this unit of reaction has the stoichiometry of 2 aluminums adding to 3 mercury, mercury 2 plus ions. This whole thing is 1 mole of reaction, regardless of the stoichiometry, as long as the stoichiometry is the lowest possible stoichiometry without having fractions. That's per mole of reaction. Okay, so back down to this equation. We're putting our 6 in here for electrons, and then Faraday's constant is this number here, which you would get on an exam. The units for this are coulombs per mole. Okay, and then the standard cell potential is 2.51 volts. So if I multiply all that together, what I end up getting is negative 1.45 times 10 to the 6. And let's talk about units. So if we combined our units, we would get coulombs times volts per mole. It turns out that coulomb volts are the same thing as joules, which makes sense because coulomb is charge and volts are the cell potential, and if you multiply those together, you would get the work done, which has units of energy. So that's how you get to joules per mole for this, which we know are the units for delta G because it's an energy quantity. So that's delta G, and we can look at the sign and say, well, that's a spontaneous reaction, and then we can feed it into this next part, which is talking about what is K. And for K, for that calculation, we need an equation that equates, that takes delta G and feeds it into our K. So that one is delta G naught equals negative RT ln K. Okay, so this is going to, so we've already calculated delta G. We know R is a constant. We know the temperature is, we're going to assume it's 25 degrees Celsius for all of these calculations. So from that, we should be able to get K, the equilibrium constant. And this is an equation that we learned in chapter 14. So we're just applying it to this situation where we just happened to have used the cell potential to figure out delta G. Okay, so what we have to do is we have to rearrange this equation to isolate K. And if you do that, you get K equals E to the negative delta G naught over RT. Okay, how did I get there? Well, I start by dividing both sides by negative RT. So I can, an intermediate step here would be this. Okay, and then to get rid of this natural log, we take both sides to as powers of e. So that's where the e to the negative delta g over RT comes in, and e to the natural log of k. Well, the natural log and the e cancel each other out, so it's just k. So that's how we get this simplified equation here. Okay, so now it's just a matter of substituting everything in. We get k equals e to the negative delta g, so negative of r, negative 1.45 times 10 to the 6, 10 to the 6th joules per mole, over r, which we use the thermodynamic value of r that has joules in it to cancel out the joules in the top. And that's 8.3145 joules per mole Kelvin. And then times our temperature, which is always in units of K, and we know that it has to be K because K is in our ideal gas constant, and so that's 298 K. If we're using standard cell potentials, we're at 298 K. So all of this whole thing here is all a power on E. I know it doesn't look like it the way that I wrote it, but it's all a power on E. And so I'm going to take that, if I do that calculation, then what I get is K equals E to the 585th, to the power of 585. And so if I calculate that out, it ends up being 1.15 times 10 to the power of 254. It's a gigantic number. So really what this is telling you is that this isn't really an equilibrium. It's just going to the right. I mean, there's going to be little to no reactance in this. It's going to go pretty much all the way to the right. So that's how to get K from measuring cell potentials, is you first calculate delta G, and then you feed delta G into the negative RT ln K equation.